Batya, who's going to talk to us about the approximate implication and applications in PGMs and relational data.
Thank you. Thank you for the invitation. Okay, so I will start with some background. Before I talk about approximate implication, I will talk about its exact counterpart, which I'm sure many of you are familiar with. Its applications broadly in artificial intelligence and relational databases. I will then describe the approximate implication problem and our results, some of our results on this. This is largely joint work with Dan Su-Chu. And then in the time I have left, I will briefly discuss an application of some of these ideas in a problem that basically comes from relational databases, but has many parallels also for probabilistic graphical models. And in particular for learning structure of graphical models, it will have a lot to do with it. Okay, so I'll start. So I don't have to say a lot about conditional independencies. We know that this is important in graphical modeling. Basically, conditional independence relations are precisely what enables this low-dimensional representation of complex distributions and allows for efficient inference and learning. In this talk, we will characterize as known that we will say if x, y, and z are three disjoint sets of random variables, then we can say that x and y are conditionally independent given z if the associated conditional mutual information is 0. So I want to say that conditional independence actually has an important part also in data management, specifically when you define schemas for relations. So I will not be very technical about this, but I think you will get the idea. I will try to show this by an example. So here we have a very simple example of a relation. A relation has attributes and values, the tuples in the relation. And the way in data management, we define certain integrity constraints, which are kind of rules, which are sentences in first order logic, which basically define when the content of the relation is consistent. Okay, so what this rule says, and the syntax is really not important, is basically that we can partition or decompose this relation into two sub-relations, okay, as you see here, where the intersection between them in terms of the attributes is this set AD. Okay, so these are the two projections of this relation on the subset of attributes ACDF and ABDE. Notice that AD is common to both. And we are going to say that the relation abides to this rule, okay, or is consistent with this rule, if when we take the join of these two relations, we get the original relation back. So in the sense, it is like this lossless type of decomposition. And this is very important. This is really a fundamental property in relational databases. It allows us to enforce data integrity, correctness, and consistency. And one of the important things that it does, it allows us to minimize redundancy. It is, in a sense, it can make the data, we can represent the data in a much smaller space. So it is also can be a form of compression. Okay, so what is the relation between the two? And basically, why does this define a conditional independence for relational databases? So we can define the empirical distribution of a relation as the uniform distribution over the tuple. So for example, here, this is what we see. And basically, if this rule holds, then it will not be surprising to know that basically that we have this conditional independence that holds in the empirical distribution. Basically that in this case, B and C are independent given A. And this really can be, maybe it is quite intuitive. And indeed, in 1987, it was shown that if we fix a relation and its empirical distribution, then a functional dependency, meaning, for example, here, A functionally determines B, if and only if the conditional entropy B given A in this empirical distribution is 0. And this multi-value dependency, this ability to decompose the relation into two parts, holds if and only if the conditional mutual information is 0. So here we have basically a kind of conditional independence for relational databases. So what is the implication problem? So we start out with a set of conditional independence relation. We're going to call it big sigma. And we have another conditional independence that we call tau. And we're going to say that sigma implies tau if for any joint probability distribution P, If each one of the conditional independence relations in sigma holds in P, then tau holds in P as well. Okay, and this problem was studied both in the AI and the database communities. In the AI community, the work by Geiger and Perl, and in the database community, slightly earlier, in the late 70s and 80s. Okay, so this seems like this really theoretical problem, but it is actually something that we encounter all the time, because actually, for example, this separation is a form of implication, right? Basically how? So here we have like this toy distribution, and we know that we construct the Bayesian network using what is called the recursive basis, right? This basically says that for every random variable, it is independent of some of its non-descendants, some of those that appeared before it, given some subset. So for example, here we see an example of the recursive basis. And this separation allows us to derive additional conditional independencies. For example, this separation here would tell us that given x2, x1 is independent of x3 and x4. This was not in the original recursive basis, but it is derived from this. And the known theorem states that this process of this separation is both a sound and complete system for inferring conditional independencies from this recursive basis. So we see that basically this separation is a form of exact implication. Okay, so before I go on, I will just define some notation. So in what follows, we consider a joint probability distribution P over n random variables. All of the sets of random variables, we assume that they are disjoint. We're going to say that a conditional independent statement is saturated if the union of these sets is the entire set of random variables, and it is marginal if Z is the empty set. A functional dependency is simply a special type of conditional independence. Okay, so, and it can be seen like this, that conditional entropy is 0 if and only if this mutual information y given x is 0. Okay. So what is known about the exact implication problem? So we know that there's a polynomial time, sound and complete decision procedure that is based on the semi-graph-aid axioms under the following conditions. When sigma is a set of saturated conditional independencies, a set of marginal conditional independencies, and tau is marginal. When sigma is the recursive basis of a Bayesian network. And I will mention that there's always an extension of this when it is the recursive basis and a set of functional dependencies. And maybe the last one that is known is when sigma has cardinality 2, meaning it contains exactly 2 conditional independent statements. On the other hand, there is also a negative result. It is known that in general, there is no finite axiomatization, meaning in the general case, when no assumptions are made on sigma, there does not exist any finite set of axioms that can derive all of the conditional independent statements that hold in a distribution. Okay, so, and this is also well known. Okay, so now that we basically have understood what the exact implication is, I will describe approximate implication and some of the motivation. So basically all of the system, what I showed you up until now, this separation and everything that is done, is basically it assumes that the conditional independence is holding the exact sense. Mainly if the associated mutual information measures are 0, then we can derive these additional conditional independencies. Okay. However, most structured learning algorithms actually derive these conditional independencies from data, and we cannot really expect them to hold exactly. We can think about them, maybe this conditional mutual information is not very big. It might be up to some threshold epsilon, but we cannot always assume that it is 0. And this raises the following question. What happens when we drop this assumption that the set of conditional independencies in sigma hold exactly 0? And basically, what guarantee can we provide on the consequent in such a case? Okay, so I will now describe the approximate implication problem and some of our results. Okay, so we've seen the definition of exact implication. And so we are now going to define approximate implication. So we're going to say that sigma approximately implies tau if for any joint probability distribution P, the associated conditional mutual information is bounded by a linear combination of the mutual information values in sigma. meaning we have some lambda, some positive lambda, such that the associated information-theoretic measure associated with tau is at most lambda times the sum of conditional independence measures in sigma. Okay, and we want this, just like for the exact case, we want this to hold for any joint probability distribution. And basically the first question we are asking is, if we have exact implication, is it necessarily the case that we have approximate implication? Okay, mainly if the conditional independencies in sigma almost hold, can we say that tau also almost holds? And for this, we would need to prove an inequality, this one. And if the answer is positive, basically we have this notion of safety. Then we can say that if the answer is positive, then the current systems that we have in place for inferring conditional independence can be used for inferring approximate conditional independence. So note that this is actually not quite enough, because this lambda here can be very big. We want to be able to bound this lambda, right? If it is very big, then basically we did not do too much. So what we need to do, we need to prove a bounded inequality. We want to prove an inequality where lambda is not very big. And then this raises, yes, I'm sorry.
I just wanted to clarify. So in the definition of approximate implication, was there assumptions on lambda?
No, so in the approximate implication, we just say there is this there is the a finite lambda. But what I am saying here is that for practical purposes, we want lambda not to be very big. We want to be able to prove this. Okay, so this is what we want to show, and basically we will see that we need to make some assumptions here. Under what conditions can this bounded inequality hold? Under what conditions to sigma, and under what conditions to tau? Notice that the other direction is immediate, right? Because if h of sigma is 0, then h of tau is at most 0, and it is always positive. So in a sense, we can also say that approximate implication is in fact a generalization of the exact counterpart. Okay, so it might seem intuitive that this would hold, but actually this is not the case at all. So in 2013, in this paper by Kasad and Romashchenko, they showed the following exact implication. It is a very simple exact implication over even just 4 random variables. So this exact implication holds. However, for any lambda, we can devise a probability distribution in which this inequality holds. So we see that approximate implication does not necessarily hold, even for these simple distributions. Okay, so this is not something that we can hope to say for in the general case. Okay, so what are the results that we have? And indeed, as I showed, we need to make some assumptions on sigma and tau in order to be able to say something about this. So the results we have are as follows. So if sigma is a set of saturated conditional independencies and functional dependencies, and tau is a functional dependency, then we have this inequality, basically with a lambda that is equal to 1. If we drop the assumption on tau, it can be any conditional independence, then this bound goes to the cardinality of the set A times the cardinality of the set B. So if each of A and B are singleton variables, this is again 1. Okay? If sigma is the set of recursive bases, the set of conditional independencies used to construct the Bayesian network, then again we have a bound of 1, and we also prove that this is tight. This bound is basically tight. If sigma is the set of marginal conditional independencies, tau is any conditional independence, not necessarily a marginal one, then we again have this bound of the cardinality of A times the cardinality of B. And as we showed in the general case, we cannot make any assumptions. We cannot say that even lambda is bounded. And I will mention that this bound of the cardinality of A times the cardinality of B is open. It might be lower. Okay, so what I will want to do next, I will try to.
You have no lower bound, no one, or
here, this one.
would you say that it's open? You mean that that's just an upper bound, but it could be 1?
It might be 1. It might be 1. It could be lowered. Yes. Okay, so I want to give some intuition on how we prove these inequalities, and so this is what I will do next. I will show a very simple proof for a very restricted setting. Okay, and this is what I plan to do next. So for this, I will need the following definition. What is an entropic function? An entropic function simply is the following. So we have a probability distribution, and we define a set function from subsets of variables to their joint entropy. Okay, so every function that given a set of random variables maps them to their joint entropy is called an entropic function. Okay, and this is the notation we call alpha is a set of indices, and H of alpha is simply the joint entropy of the joint random variable that is defined over this subset of random variables. And I will really digress just for a second here and say that characterizing this set of functions is a major open problem in information theory. It is also known in a result by Matus that there is no finite set of inequalities that characterize this what is called this entropic region. So this is currently uncharacterized, but this is the definition. Okay, so what is the technique we used for the proofs? So for the proofs, we rely on what is called the I-measure theory. This is a theory that was developed by Raymond Young in the early 90s. What it does, it establishes a one-to-one correspondence between Shannon's information measures, such as entropy and mutual information, and set theory. And so the strategy of the proof is to first characterize exact implications by conditions on this measure of entropic functions, and then use this characterization to prove the inequalities. Okay, so in order to really explain the proof, I will have one slide on the I-measure. Okay, so we have a joint probability distribution. We associate a set that we call M of xi with every random variable, and we have the complement set, MC of xi. Again, so we have the joint random variable x alpha, and we denote by M of x alpha the union of the sets in the indices of alpha. F of n is simply the collection of sets that is obtained by any sequence of set theoretic operations over this set: intersection, union, complement. The atoms of Fn are simply the intersection of all of the yi's over all of the random variables. So yi is either the set associated with xi or its complement. Mu, which is a function from Fn to the reals, is a signed measure. If it is set additive, meaning if A and B are disjoint, then applying mu to their union is their sum. And mu of the empty set is 0, and this is expressed as having that mu of the atom that intersects only the complement sets is going to be 0. And finally, the I measure is defined as follows: mu star, it is denoted by mu star, of the set associated with M of x alpha is going to be the joint entropy H of x alpha for every subset of indices. So this is basically the I measure. Okay, and the theorem by Young says the following, basically, that this mu star is the unique signed measure on Fn that is consistent with all of Shannon's information measures. Okay, what does this mean? So if we have, for example, here a set of 3 random variables, it means that this region, if you apply the mu star to this set, it's going to be the conditional entropy. This region is going to be the joint mutual information. This part is going to be conditional mutual information, right? It is the intersection of the sets associated with x2, x3, and complement of x1. Finally, notice this part. So this is a mu star of the intersection of all of them. And this does not correspond to any information theoretic measure. Okay, so it does not necessarily mean that everything is going to correspond to an information theoretic measure. And I will get back to this. You will see why this is important. Okay, so in order to provide the proof intuition, I will restrict myself to talking about only those probability distributions that have a positive I measure. This is a very heavy restriction, but I make it just to kind of show the intuition behind the proof. Okay, so this is what we are going to do. And basically, why am I doing this? Because it is known, it was shown that if we define we define an I measure where everything is always positive, basically we can think about assigning a positive value to all of the atoms, then it is necessarily we are going to have something that represents an entropic function, meaning it's going to correspond to a probability distribution. Okay, so this is a theorem by Jung. I will also say that although this is a very heavy restriction, there are certain applications that arise in which these functions are relevant, especially in the analysis of constraints in market basket analysis, which is important in data mining.
This is not an if and only if, right? So
This one?
the Jung's theorem is
No, so Jung's theorem say if it is positive, then it is entropic. No, it's not if and only if. You can have entropic functions where it is negative. Yeah. So, but this is just my restriction in order to show it. Okay. So in this case, we can almost immediately say that we have approximate implication with a lambda equal to 1. Why is that? So if we have exact implication, then it must be the case that the set associated with tau must be a subset of the set associated with sigma. Now, why is that? Suppose it is not, and the figure here, it's a little too light, but so suppose it is not, then I can say, okay, I'm going to assign every atom in sigma the value 0. I'm going to assign some atom in tau to have a strictly positive value. I'm going to assign it the value 1. And then basically we see that the I measure associated with sigma is going to be 0. The I measure associated with tau is going to be non-zero. And we immediately arrive at a contradiction of the exact implication. So if we have exact implication, we have to have this subsumption. It must be the case that the set associated with tau is a subset of the set associated with sigma. And since everything is positive, then we get the inequality. So we see that for the set of this family of probability distributions, we immediately get a one approximation. Note in the general case, this is not going to hold. In the general case, the fact that the set associated with tau is a subset of the set associated with sigma does not necessarily mean that we have exact implication. And since in the general case not everything is positive, we're also not going to get the fact that this necessarily holds. But I hope this gives some idea of how we can use the I measure in order to prove these types of inequalities. Okay. So as you noticed, the I measure is not necessarily going to be positive, and there are really very simple probability distributions in which this will not hold. For example, for the parity distribution, x and 1 and x2 are independent binary random variables. We are going to define x3 to be their parity, and if you work out the information theoretic values, you will notice that the atom associated with the intersection of all three sets is going to be -1. So immediately see that this proof will not hold in general, which makes it, there basically lies the technical challenge in proving these inequalities. And for these cases, then the proofs are in the papers. Okay, so what I showed you is really for a restricted setting. Okay. So basically in the time I have left, I will discuss an application of these ideas of thinking about mutual information in the approximate sense. Okay, and I will start. So here I'm going to go back to this decomposition of a relation, but I will show how this relates basically to junction trees, which you are familiar with. So here I showed you before how I can decompose a relation to two relations, but basically we can decompose a relation into any number of relations. So for example, here I decomposed R into these four sub-relations that you see here. They can be organized in this tree, okay? And basically, we're going to say that this schema, soon I will say what you've done, this schema holds in R if when we take the join of these four relations, we're going to get the original relation back, okay? And this is again defined in a strict sense. When I take the join, I must get the original relation precisely as it is. But now imagine what happens. I'm going to add a single tuple to this relation, which means I need to add a tuple to this relation BDE. But now when I take their join, I'm going to get this spurious tuple, this tuple that wasn't there anymore. And this is basically saying that this schema is now lossy. It does not fit the data anymore. And basically, because of this single tuple, my schema is going to be invalidated now. Okay, so it's not going to hold. And basically, the goal of this work was to discover all of the approximate acyclic schemas that hold in R. And I will soon define what approximate means, but in a sense, we want this number of spurious tuples not to be too big relative to the set of tuples that were in the original relation. Okay, and why are these important? So in the database community, it is quite well known that if the query has this tree-like structure, then you have an efficient algorithm for evaluating queries over the of evaluating queries. This is the famous algorithm by Acyclic from 81. More recently, it has been shown that the databases that have this structure allow for speeding up machine learning applications over relational data. Machine learning algorithms also work a lot over relational data, and if the relational data is organized in such a schema, then there's work that shows that they can be, the performance is much better. Okay, so what is so you might have noticed, what is so special about these acyclic schemas? They are basically join trees, right? In a cyclic schema, we have the bags, we have the running intersection property. Each one of the edges basically represent the saturated conditional independence, right? So for example, here the edge AD, what it means is that these two sets of variables given AD become independent. Or we can say that this joint dependency holds. Okay, so for an acyclic schema, I will denote by Ci of S the set of saturated conditional independencies that are represented in this structure. Okay, and a well-known theorem, this is again, you can easily see the equivalent in graphical models that basically an acyclic schema S is equivalent to the set of conditional independencies that are represented on their edges, right? Basically, if each one of the conditional independencies is represented by the edges hold, then the entire relation abides to this rule of the acyclic schema, just like if a probability distribution, each one of the conditional independencies represented by a junction tree hold, then the distribution can also be represented using this junction tree. Another thing that is known is that the number of these conditional independencies is at most the number of variables in the distribution, right? The number of clusters in a junction tree is at most the number of variables in the distribution, and hence this number of conditional independencies is also at most n. So given this, the strategy we can, I'm sorry, there was a question? So given this, the strategy we can take is as follows. We will discover all of the saturated conditional independencies that hold in the relation, and then use these to synthesize all the possible schemes that hold in the relation. Okay, so now, fortunately, the second bullet here is more or less a solved problem. For this, we basically need two things. We first need to be able to characterize the set of conditional independencies that can be combined to an acyclic scheme, right? We can say there's an exponential number of conditional independencies that hold in a distribution, but there is only a linear number that live together in an acyclic scheme. So, and fortunately, this is actually this characterization is known. It was studied in the database community. It was studied in the graph theory community. And so this is, we know how to characterize these sets of conditional independencies. And then we want to be able to enumerate them. And for this, we rely on the previous work of Carmeli and Kimmelfeld and myself that we showed an efficient algorithm of enumerating all of the three decompositions of basically of a distribution. So basically this second part is second bullet is solved. I will notice that what we are looking for is these approximate acyclic schemes, right? So not in the, we don't necessarily want to be able to relax this hard constraint that they hold exactly. And therefore this is going to be the challenging part of discovering all these independencies. Okay, so in what sense are we talking about that this is going to be an approximate? So for this, let's consider a little bit about the information theory of these acyclic schemes or of junction trees. So here we have an information theoretic measure that we denote by J. It is simply the sum of entropies associated with the clusters of the tree decomposition minus the joint entropy associated with the edges, which is simply the intersection of the two endpoints, minus the joint entropy of the entire set of variables. And unsurprisingly, in this same paper by Lee in 1987, he showed an acyclic schema holds in the relation if and only if this measure is zero. And I remind you that these entropies are taken over the empirical distribution associated with the relation. So how is this related to graphical models? So recall that the distribution associated with a decomposable model that has a junction tree is the product of marginals associated with each one of the clusters divided by the product of the marginals associated with each one of the separators. And what we have shown is that this J measure is precisely the KL divergence between the distribution associated with the joint tree and the original distribution, this empirical distribution. So it is not surprising that when this is zero, we get precisely what we want. We get this exact, that this rule holds exactly. So in the approximate sense, what we will want to do, right? We're going to say, we're going to relax. We're going to say, okay, we are not going to make this J measure precisely zero. We want this J measure to be some small value, some epsilon. We're going to say this acyclic schema approximately holds if this J measure is at most epsilon. So, right, we know that if each one of the conditional independencies holds in the distribution, then we can say that the schema holds exactly in R. But what about the approximate case? Does this still hold? If each one of these conditional independencies holds only approximately, what can we say about the extent to which the schema holds in R, or that the joint or that these three decompositions really fits this distribution? Okay. So the answer is yes. It is slightly more subtle though than in the exact case. So what we prove is the following. If for example, we put a threshold on the extent to which these saturated conditional independencies hold in the distribution, then we can show that this J measure is at most linear. It's going to be at most n-1, where n is the number of variables, times epsilon. Okay? So in a sense, we have this positive result that we can combine these in a strong information theoretic sense. We can combine these conditional independencies into this decomposable distribution. So this would be the strategy: discover all these saturated conditional independencies that almost hold, and from those enumerate all of the acyclic schemas, or all these decomposable representations of the distribution. So I will not describe the solution, but the main idea is that there's an exponential number of these saturated CIs. However, many of them are redundant, in the sense that many of these conditional independencies can be derived from others. So we don't need to really mine all of those that can also be derived from others. So in the paper, we characterize a core set of conditional independencies that is complete in the sense that any other conditional independence that holds in the distribution can be derived from them using the semi-graphoid axioms. And then we apply all kinds of pruning techniques based on these ideas and based on information theoretic inequalities. So we also implemented this. Mining algorithm, and as I said, basically, what in the data management community, the interest is in the error, in the sense of the number of spurious tuples that are generated. So what we wanted to see was how does the error which is basically the percentage of spurious tuples generated when you take the join. How it relates to this savings in storage, or to the extent of the compression that we get from the fact that we eliminate a lot of redundancy when we perform this decomposition. Okay, so naturally we want to bring the error down, and we want to increase the savings in storage. And here you see the algorithm was able to extract something like more than 400 decomposable models for this distribution. And the nice thing is that you can see that if you are willing to incur an error, for example, of even about 10%, which is not too much, you achieve an almost 80% savings in storage. So you can think about it in practical sense. We can save these spurious tuples, but on the other hand, get very large savings in storage. Okay, so I will conclude at this point. The interesting thing is really to see how these ideas can really be applied to learning the structure, or specifically learning decomposable models of probabilistic graphical models. And one distinction between that we have in relational databases as opposed to distributions is we assume in the data management sense that we have the precise description of the distribution. I have this empirical distribution and this is what I have, okay? But in the general case, we assume that we only have samples from the distribution, and then we cannot really compute the conditional mutual information exactly. We have these estimates of it, and it is not clear how to define the approximation in this sense. Broadly, what we're looking to do is optimize over this set of acyclic schemes. We are currently able to quite efficiently enumerate all of them, but we would like to be able to optimize over this set. Broadly, for example, one of the things we are looking for is if given some threshold, right? I'm looking for a distribution that is at most some threshold away from the original one. I want to find a cyclic scheme that leads to the largest compression, for example. I will mention here very briefly that if we assume that the distribution is strictly positive, then we can do much more sophisticated things here. One of the things that also we don't have in the relational database sense is we cannot assume this positivity that we saw this a lot in this workshop, where we assume that the joint distribution is always strictly positive. So we can do other things. This does not hold in the relational database sense. And another thing we're looking at is exploring this connection between the KL divergence and the number of spurious tuples. You would assume that this would be monotonic, that this would be always be monotonic, but it is not the case. We can have two schemas, one where the KL divergence is smaller than the other, but it will have more spurious tuples. So we're looking to really be able to answer the question. Suppose a user says, I'm willing to incur an error of 10 spurious tuples. What is the threshold that I should set? So this is also something that we're looking at. Yes.
When I think of database applications, I normally think of like banking or healthcare, where it's like super important to kind of maybe have all the records correctly in the database. Can you, all of the records, or like correctly in the database? Can you give some examples of like applications where you'd be okay with, you know, some error in order to have like compression?
So in cases where basically in data warehouses, where basically, for example, you use the data to answer queries or to make predictions. So you know that in any case your prediction will not be very accurate, but it can save you a lot of memory, a lot of space, a lot of running time if you have the data in a compressed form. And even if you are willing to incur an error, you can think about, instead of just representing the data in a table, then you can represent them in this decomposed table and also save the error itself. And then when you process a query, you take into account that you have these error tuples that you somehow need to discount their effect on the query result. So in any case, it can be, even for exact applications, it can still be beneficial.
Super interesting talk. So lots of questions, but I have just one for now. So when we do causal discovery, then as you said, we do often use methods with using conditional independence tests all the time and try to piece together the underlying algorithm, the underlying graph from those independence tests. So in that case, the independence tests are often of a parametric form, right? That they'll assume Gaussianity or some sort of form. So while your results were completely general, right, with the mutual information. So what I'm wondering about is that, do you see a straightforward or easy way to include these sorts of parametric background constraints that I might be happy to make about my distribution into these results?
So yeah, it's a really good question. I don't know in this case. I don't have a good answer about what. I'm sure we can make this connection between statistical testing and the mutual information itself. At the time I tried to look, I did not find any place that says if the statistical test gives such and such a result, then the mutual information. So I don't even know what would be the relation between the two. But yes,
can I just follow up? Then the other way around is that, you know, the example you gave was a parity case again, and to me, that always seems like, okay, this is the degenerate kind of case that we use to prove certain things are impossible. But really, if that's what I have to worry about in practice all the time, then I'm going to be doomed. So do you have a sense of these sorts of impossibility results deriving from really peculiar distributions, or where I'm going to say parity is a peculiar one?
So no, this is really an extreme case, but basically in any, you will, these non-positive I measures will arise in any case where if you add additional variables to your conditioning set, you will not necessarily have still conditional independence. So even in the Bayesian network structure, when you have a converging, then we will have this negative. So this is really an extreme case that I showed for the example, but it can.
So like if you had a threshold function, if we had a threshold, if we took the sum, but so it was a monotone dependence, you could still create this negative.
Yes. So
well, that's your favorite kind of collider, like a monotone, like I'm taking the sum and threshold.
If I can assume on my distribution that each time that I add to my conditioning set, I will not get a larger conditional mutual information, then I can immediately say that I will have this lambda equals 1. But this is, I think, quite restrictive. It does not, don't see how it really happens about it. Each time you add to the conditioning set, you cannot get that. Yes.
So this is kind of building off of Frederick's question. Instead of putting parametric assumptions, you can add axioms, right? Like upward stability or composition or things like that. Is there anything known about what happens when you move beyond the semi-graphoid axioms for either the exact or the approximate implication?
So if you assume if we assume strict positivity of the probability distribution, then we also have the intersection axiom, and then basically the algorithm that I showed for finding these conditional saturated conditional independencies can be made much more efficiently. Basically, it can be translated into a purely graphical algorithm. The results I showed here, in a sense, are general in the sense that they hold for polymatroids. They will hold for any function that is submodular and monotone. So in that sense, it is quite general. If there are specific additional constraints, then maybe we can make this type of algorithm much more efficient.
I guess sort of following up on that, in database applications, how important is it to have these types of implications for any semi-graphoid? So like, is it really important to consider the set of all possible distributions in database applications?
So you can, as I said, you can't assume that you can have the intersection axiom because there's a lot of determinism in the database applications. We have these very strict integrity constraints that are defined using first order logic sentences. So we can't assume that. Maybe there are other assumptions that I'm not aware of that we can think about or be happy to discuss, but there's not something that I'm aware of.
Maybe I misunderstood something, but your sigma is just independence constraints.
Yes.
So if I included constraints that bounded the mutual information between the variables away from zero, so ensured a certain dependence between variables, then presumably that would help the kind of implications that I could reach about what sort of other dependencies and dependencies are implied.
So I don't know of any result regarding saying that a pair of variables are dependent. We only look at the independence. So I would guess that if one of your sigma is above some threshold, then this is basically only a lower bound. So I don't know, but again, it's also an interesting question to say, you're asking about the other direction, you're asking about an upper bound.
So the reason I asked is because when we do constraint-based causal inference, we often have conflicted set of independence and dependence constraints such that there is no directed acyclic graph that fits all of them because we've had measurement error along the way. And so one of our independencies or dependencies was misestimated. And so then the question is like, okay, well, what do we do about this sort of, about resolving this sort of conflicted set of tested states?
So one thing that comes to mind is that what if instead of learning this Bayesian network or a causal model, you go through this stage where we first learn a decomposable model. Basically, we only learn a junction tree. And then I think maybe in that sense, it can be, we can say, I would imagine, this is really like very intuitive thinking, but say, okay, if for some set of random variables we know we have a strong dependency between them, we're going to force them to be in the same cluster. And then it basically reduces the problem to defining the directed edges in each cluster on its own. So I think the way to maybe utilize these types of general results is to go through, use it to reduce the problem instead of looking at other variables, to looking at the variables in each cluster. So thank you very much.
Yeah, there's a break now.